Now let's look at examples that have only 3 electron domains. Take, for example, borane. It's the simplest compound of boron. Boron has 3 valence electrons in the 2s and 2p subshells. And by this arrangement of electrons, we would predict that boron could only form 1 bond because it has 1 unpaired electron. However, we know experimentally that borane is the simplest compound of boron. It has equivalent bonds and bond angles. So we have to, again, think about modifying this, and we can excite an electron from that 2s to the 2p sublevel. So now we have the 3 unpaired electrons to form those 3 bonds. However, they are not going to be equivalent bonds, right? We'll have the same situation we had with methane, where we have overlap with a 2p orbital versus a 2s orbital. Those are not going to be the same. So we imagine hybridizing or mixing them as we did before. In this case, we only need to mix 3. Okay? We only need to mix the 3 orbitals that are going to be involved in chemical bonds. So by this, we would end up with 3 equivalent or degenerate orbitals, and those would be called the Sp2 hybrid orbitals, and this 2p orbital remains unhybridized. So the energy of the Sp2 is going to be somewhere between the S and the P because it's a mix of the two. It will lie in between there. And the 2p energy doesn't change. When we fill our orbitals, starting with the lowest energy first, we fill those Sp2 orbitals. And now we have 3 equivalent atomic orbitals that have been hybridized to form those 3 equivalent bonds and give us the experimental structure of borane that we observe. So when we look at this in terms of the balloon pictures, we can see that there are 4 total orbitals on borane. This 2p orbital is still there. It just happens to be empty. And remember when we talked about the reactivity of borane, when we were talking about systems that have fewer than 8 electrons about their central atom, there has to be a place for those electrons to go when it reacts with something. So water, having the lone pairs, those electrons can get donated into this 2p orbital. We see a rehybridization, so this borane water complex that we saw form in that reaction actually is going to have the geometry, or excuse me, hybridization about the central boron atom. Because it now has 4 domains, the hybridization has changed to reflect that and is now Sp3 hybridized. Okay, so you have to look on a case-by-case basis, but again, just to point out that this is a region of space that can be occupied by electron density. So the space is there, it's just not filled when we're talking about ordinary borane. We can also use hybridization to explain the bonding in systems that contain multiple bonds. Take, for example, ethylene. This is a carbon-containing compound that has a carbon-carbon double bond. And the double bond here consists of a sigma bond and a pi bond. So there will always be 1 sigma bond connecting 2 nuclei, and any second or third bond must be a pi bond. So we look at this in terms of steric number. The steric number is 3. It has 3 groups about that central atom. And then we can think about it in terms of hybridization. Well, those 3 bonding groups about the atom need 3 hybrid orbitals to bond with, okay, to form those 3 sigma bonds. So we start with our S and P configuration. I'm going to go ahead and just skip to the excited state here. And then we hybridize them, right? So carbon has 4 electrons. We're only going to hybridize the ones that we need for sigma bonding. So that's 3 sigma bonds. And we'll get the Sp2 hybrid, and that 2p remains unhybridized. So we end up with this arrangement of electrons. We have 3 sigma bonds that are all equivalent angles away from one another. And then the 2p has that electron in it that can be used to make that second bond. So when you think about drawing this, we have this overlap here of an sp2 orbital. Because both of these carbons are the same, I essentially have figured out the electron configuration of both of those carbon atoms. They will both have 3 sp2 orbitals and 1 2p orbital. So the sp2 orbital overlap will be my sigma bond, and then there will be an sp2s orbital overlap. That s orbital is from hydrogen. It only has that. Right, this is an sp2 with an s orbital. And then the carbon also has that p orbital, right? And this p orbital will overlap with the p orbital on the neighboring carbon. And in my drawing here, it's kind of hard to see that these are close enough to overlap, but this side-to-side overlap, both above and below the plane, constitutes 1 pi bond. Okay, even though it overlaps above and below, so we see we have our 1 sigma bond, our 2 sigma bond, and our 3 sigma bonds, and then our 1 pi bond about that in ethylene. Thanks for watching.